Okay, we need to develop some more techniques before we start computing the scattering amplitudes. Yesterday we have introduced the S matrix, which is given by time order product of e to the power minus I integration minus infinity to plus infinity dt h I of t. What we will do today is we will develop some more techniques which relates the time order product of various operators in terms of the normal order product, because it is more convenient to evaluate the matrix elements of any operator which is given in terms of normal products instead of time order products. So, let us do that. To do that, what we will do is we will rewrite this S matrix in a slightly more convenient way. So, let us consider this to be the limit T I going to minus infinity, T f going to plus infinity time order product of e to the power minus I T I to T f dt h I of t. Now, what you do is you take this interval T I to T f and you divide it into n parts. Okay. So, let us say this is T I, this is T f, you divide it into n segments, each of them with length, let us say delta t. So, n equal to or delta t equal to T f minus T I divided by n. Then this integration you can write it as a sum of these values h I at the midpoint of each of these intervals times the length of the interval in the limit when the size of the interval is very small, it is an infinitesimal quantity. So, therefore, this integration here is nothing but this is limit T I goes to minus infinity, T f goes to plus infinity, time order product of e to the power minus I times delta t times h I of T n plus h I of T n minus 1 plus so on h I of T 1, where T n is the midpoint here of the first interval, T n minus 1 is the midpoint of the second interval and so on, and T 1 is this point here. So, this is what it is, but now we will use this relation e to the power a e to the power b is equal to e to the power a plus b plus half commutator of a and b whenever this commutator commutes with both a as well as b. So, if commutation of a with a b commutator equal to 0 equal to commutator of b with a b. In our case, the commutator of h I with itself at different times is a C number. So, therefore, this relation is true. So, what we will do is we will take this expression e to the power minus I delta t h I of t 1 and so on h I of t n h I of t 1. Then what I will get here is I will get e to the power minus I delta t h I t n e to the power minus I delta t h I t n minus 1 and so on. There will be commutators, but I will not write commutators because I am considering the time order product here. Okay. So, the time ordered product of commutators becomes 0 because t of some a of t b of t prime is same as t of b of t prime a of t. You just use the definition of time ordered product. It does not matter in what order you write operators inside the time ordering. Therefore, time ordered product of commutator of any two operators a of t b of t prime becomes 0. So, because this operator here is within the time ordering, so I am allowed to do this, and here e to the power minus I delta t h However, the quantity inside the bracket is actually already time ordered. The reason is that I am considering this interval where this is, let us say this is called T f and this is T I. So, T f is greater than T I, T I, T f is greater than T I, this is T n. Therefore, I have this ordering that T n is greater than T n minus 1 and so on is larger than T 1 according to my convention. So, therefore, this is already time ordered. So, I do not need to write this time ordering. So, this is e to the power minus I delta t h I of t n e to the power minus I delta t h I t n minus 1 so on up to e to the power minus I delta t h I t 1. So, the time ordering is gone. Now, what I can do is I can again use this relation here, and when I use this relation and I will keep all the terms up to order delta t square. In that limits, this is simply e to the power minus I delta t sum over I running from 1 to n h or k running from 1 to n h I of t k, the sum of all these terms times e to the power half minus I delta t square and sum over k greater than L h I t k h I t L commutator. Okay. So, this is what you get. Now, I will take the limit n going to infinity and hence limit delta t goes to 0. In that limit only this is valid because I am keeping all the terms up to delta t square, and then in this limit I can convert all these sums into integrations. When I do that, what I will get for this S matrix is the following. I will also take Ti and Tf to be respectively minus infinity and plus infinity. So, in this limit this is given by e to the power minus I minus infinity to infinity dt S I t, and then e to the power minus half integration dt dt prime commutator of h I t h I of t prime, but that is not sufficient because here I have to impose this restriction here that is equivalent to imposing theta of t minus t prime. So, what I did is I started with time order product of e to the power minus I minus infinity to infinity dt h I of t, and then I rewrote it in this form. Okay. It is quite trivial. I mean, this is the sum of delta t times h I of t k is obvious. What you can do is you can similarly write it, you can divide this integration into small intervals, and then you can write it as sum, and then you will get the second term in the exponential. Typically, we are considering field theories where the interaction Hamiltonian is written in terms of integration of d cube x times some Hamiltonian density S I of x t. So, in this case this quantity here becomes e to the power minus I d4 x h I x, and here e to the power minus half d4 x d4 y theta of x 0 minus y 0 commutator of h I x h I y. This is the S operator, or this is the S matrix. Now, we will consider a specific example. We will consider the example of a real scalar field of mass m. So, the action or the Lagrangian density, the free Lagrangian density is given by half del mu phi minus half m square phi square. I will consider an interaction of the type Li is minus j of x phi of x, where j of x is a classical current So, the quantum field phi is coupled to some classical current. I am considering one specific example, which is one of the simplest cases that you can study, where the interaction term is of this kind, where the quantum field phi is coupled to some classical current J of x. In presence of this interaction, we will consider the S matrix and then we will write it in a nice form, which will be useful for our purpose. So, let us consider the S matrix now. The interaction Hamiltonian H I of x, interaction Hamiltonian density is J of x times phi I of x, where phi I is the quantum field phi in the interaction picture. I will take this Hamiltonian density and then I will evaluate the S matrix, which is e to the power minus I H I x d4 x and e to the power minus half d4 x d4 y theta of x0 minus y0 H I of x. H I is very simple form. What I will do is I will first consider this first term here in the S matrix. I will put this expression for H I of x and then I will write it in a convenient form. So, consider the first term, which is e to the power minus I H I of x d4 x, and for our interaction this is e to the power minus I plus I into d4 x j of x phi I of x. This quantum field phi I can actually be written. Is there a minus sign? There is a minus sign. Okay, thank you. So, the quantum field phi I can actually be written as phi I plus of x plus phi I minus of x, the positive frequency part and the negative frequency part of this field. So, phi I plus of x contains all the annihilation operators, whereas phi I minus contains all the creation operators. So, this is again the first term becomes e to the power minus I integration d4 x j of x phi minus x plus or minus again I integration d4 y j of y phi plus I of y. So, I simply substituted here phi minus I of x plus phi plus I of x, and then this integration will give me just two terms in the exponent. In the second term, I have used the integration variable as y instead of x. You will see in a moment why. Okay. So, this is absolutely trivial, but now again I will use this relation e to the power a plus b equal to e to the power a, e to the power b, e to the power minus half commutator of a b whenever this a b commutator commutes with both a and b. Here this is of this form e to the power a plus b. So, this quantity I can write it as e to the power minus I d4 x j x phi I minus x and e to the power minus I d4 x j x phi I plus of x, but now e to the power minus half and minus I square, commutator of this and this will give me integration d4 x d4 y. J of x is a classical field, so j of x, then commutator phi I minus x phi I plus y j of y. This is all I will get. But now you see this first two terms here, this term contains all the creation operators and the second term contains all the annihilation operators. So, this is already in the normal ordered form. So, what I can do is I can rewrite this as normal ordering of e to the power minus I d4 x j x phi I of x, because if you consider this this exponential term here and do normal ordering, this is what you will get. All the creation operators will be there to the left of all the annihilation operators. So, therefore, this the expression here is now e to the power half d4 x d4 y jx commutator of phi I minus x phi I plus y jy. All right. So, this is what I got for the first term in this expression. I have the second term. So, what I will do is I will substitute for the first term here and then let us see what we get. So, this implies the S matrix is normal ordering of e to the power minus I d4 x j of x phi of x, and then this times e to the power half d4 x d4 y j of x phi I minus x phi I plus y j of y. This is the first term, and now I will write the second term times e to the power minus half d4 x d4 y theta of x0 minus y0. Now, I know hi of x is j of x times phi of x. So, again I will have a j of x phi I x phi I y j of y. All right. So, there is nothing non-trivial that is done. I have done some straightforward calculation. You can see that you can combine these two terms and write them as a single term. So, let us do that. This is again normal ordering of e to the power minus I d4 x g of x phi of x, and then these two terms will give me e to the power half d4 x d4 y and then j of x times phi I minus of x phi I plus y commutator, and in the second term there is a minus theta of x 0 minus y 0 times commutator of phi I x and phi I y. Finally, I have the current J y. I can write this term here inside the curly bracket in a simpler form. Note that this is a C number here, and hence I can write this as the vacuum expectation value of itself, where 0 is the vacuum corresponding to the free Hamiltonian, which I have considered is normalized to 1. So, therefore, this term here phi I plus x phi I minus y commutator minus theta of x 0 minus y 0 phi I x phi I y, this is equal to the vacuum expectation value of the same term phi I plus x, sorry, there is a minus here, this is plus, minus x phi I plus y minus theta of x 0 minus y 0 Now, this I can consider the first term here, which is the vacuum expectation value of commutator of phi I minus x phi I plus y. This will give me two terms phi I minus x phi I plus y minus phi I plus y phi I minus x. However, the first of these two terms is 0, because this involves only annihilation operators, it acts on the vacuum. So, this will give me 0 trivially. So, the first term vanishes. So, therefore, this commutator here is minus vacuum expectation value of phi I plus y phi I minus x. But since phi I minus of x acting on phi I plus x acting on vacuum is 0, and also if you consider the left action of phi I minus of y, this is also 0. Therefore, I can write this as minus vacuum expectation value of phi I y phi I x. You can simply substitute phi I to be phi I plus phi I minus, and then you can see that if you use these two relations you will get here to here. It is very straightforward. So, this commutator here is nothing but minus of the vacuum expectation value of phi I y phi I x. All right. So, let us erase. So, that is only the first of these two terms. I can consider the entire thing here, that will give me phi I minus of x phi I plus y minus theta of x 0 minus y 0 phi I x this C number here is equal to minus vacuum expectation value of phi I y phi I x here, and then note that I have taken out a numeral minus sign. So, I will get a plus theta of x 0 minus y 0 commutator of phi I x phi I y, the vacuum expectation value. Okay. So, very straightforward. Now, you can see that you can write this term even in a more compact way. If you look at this, it will give you two terms. The first term is simply theta x 0 minus y 0 phi I x phi I y. The second term has a minus sign because of the commutator times theta x 0 minus y 0 and phi I y phi I x, but here you have already phi I y phi I x. So, you can combine these two terms. There is a 1 here, there is a minus theta of x 0 minus y 0. You know 1 minus theta of x is theta of minus x. This is one of the properties of the step functions. So, you use this you can use this relation, and then what you get is minus vacuum expectation value of the first term here theta x 0 minus y 0 phi I x phi I y, and this combined with the second term coming from here will give me theta of y 0 minus x 0 phi I y phi I x. But what is this? This is the time ordered product of phi I x and phi I y. So, this quantity here is minus vacuum expectation value of time ordered product of phi I x phi I y. So, what I did is I considered this exponent here in the second term for the expression for S matrix, and I have shown that this term here inside the curly bracket is nothing but the vacuum expectation value of time order product of phi I x and phi I y. So, let us write it here. This S matrix is given by normal order product of e to the power minus I d4 x j x phi of x and then e to the power minus half because of this minus sign here, and then integration d4x d4y j of x, vacuum expectation value of time order product of phi I x phi I y j of y. So, this is what we got for the S matrix here, but we already know so what we did is we started with an expression which was in the form of the time order product. Now, what we got is something in terms of the normal ordered product and then some C number. So, this is what is a normal ordered product of an operator, and then this is just a commuting number. So, let us summarize what we got. We got an important result which is time order product of e to the power minus I integration d4x j of x phi of x is equal to normal order product of e to the power minus I d4x jx phi x times e to the power minus half vacuum expectation value of time order product of phi I. There is a phi I here in both these terms because I am working in the interaction picture, phi I x phi I y j of y. Now, what I will do is I will expand both left hand side as well as right hand side, and then I will consider terms in each order of j, and then I will equate them. So, the left hand side is nothing but time order product. So, let us do it term by term. 1 minus I d4 x j of x phi I of x, and then plus minus I square over 2 factorial integration d4 x d4 y j of x j of y time order product of phi I x phi I y, and then plus minus I cube over 3 factorial d4 x1 d4 x2 d4 x3 jx1 jx2 jx3, and then time order product of phi I x1 phi I x2 phi I x3 and so on. So, this is what the left hand side gives me. Similarly, what you can do is you can consider an expansion in the right hand side and then equate terms order by order. So, let's compute it for the first few terms. So, the right hand side again will give me a bunch of terms like this. but instead of time ordering we will get normal ordering, but also we have this contribution from the second term here. So, let us see what we get. We will get 1 minus I d4 x j of x phi of x, and then plus minus I square over 2 factorial d4 x d4 y j of x j of y. Now, I have normal ordering of phi I x phi I y, and then plus minus I cube over 3 factorial d4 x1 d4 x2 d4 x3, and then j x1 j x2 j x3. Actually, here also there is a normal ordering involved in the first term, which will be important for us. And normal ordering of phi I x1 phi I x2 phi I x3, and so on, but this is only the first term. Then I will also get this times 1 minus half d4 x d4 y j of x j of y times vacuum expectation value of time order product of phi I x phi I y, and so on. Okay. So, now you see the 0th order term will not give anything non-trivial, it will just say that 1 equal to 1. Same about the first order term here, first order term will just say that phi I is equal to its the time order product and also is itself equal to its normal product, but the second term here will give me something non-trivial. Here you consider in the left hand side the coefficients of terms quadratic in J, and in the right hand side you consider coefficients of terms quadratic in J. Here you have only one term which involves time order product of phi I x phi I y. So, from left hand side I get time order product of phi I x phi I y. However, from the right hand side I get here the normal order product of phi I x phi I y, and also this term here plus vacuum expectation value of time order product of phi I x phi I y. There is no other term here which is quadratic in J except this and this term. So, therefore, I have only these two contributions. So, I got an important relation here which relates the time order product of two of the operators in terms of normal order product of both these operators and some C number here which is the vacuum expectation value of time order product of these two operators. Now, I can consider the third term here, and then again I will get a relation which is quite similar to this one. So, let us compute the third order term, and then we will specify what it is in its general form. So, the third term here gives me the coefficients of a term which is cubic in J, gives me time order product of phi I x 1, phi I x 2, phi I x 3. If we consider this right hand side here, then what you will get? You will of course get this term which is cubic in J. So, I have normal order product of phi I x 1, phi I x 2, phi I x 3. However, I will get also a contribution which is a product of this and this. Okay. So, you can see that this you can again write as integration d 4 x 1, d 4 x 2, d 4 x 3 times j x 1, j x 2, j x 3, and then there will be 3 terms here. So, you can convince yourself that this is nothing but phi I x 1 times vacuum expectation value of time order product of phi I x 2, phi I x 3 plus phi I x 2 vacuum expectation value of time order product of phi I x 1, phi I x 3 plus phi I x 3 0 phi I x 1 phi I x 2. The point is the following: you multiply this term with this term. The coefficient here is minus minus plus I over 2, but the coefficient here, as you can see, is the minus I over 3 factorial here. Okay. So, now you can write it, and then the point here is that it is completely symmetric between x 1, x 2, x 3 here. So, is this. So, whatever you will get the remaining term, it has to be completely symmetric if you do a permutation between x 1, x 2, x 3, and then that will give you 3 terms. All these 3 terms will add up, and then there will be a factor 3 factorial here, which will cancel that 3 to this 3. So, therefore, this, I mean, you can convince yourself that this identity here is true. So, this involves the time order product of 3 of these operators. Here you get them in terms of the normal order product and then the vacuum expectation value of these 3. In general, what you can do is you can introduce this idea of contraction. What you do here is, what you see here is, you have the time order product which is equal to the normal product here. Then what it does is that it picks all pairs here, all pairs of operators, and then you consider their vacuum expectation values, and then whatever is left, the normal product of that is what you get. So, in general, what I claim and what I suggest you to verify at least up to order 5 is the following. You consider let us say 4 operators, I will call them phi 1, phi 2, phi 3, phi 4. Phi 1 stands for phi of x 1, phi 2 for phi of x 2 and so on. So, this set of operators is equal to normal order product of the same 4 operators phi 1, phi 2, phi 3, phi 4, and then I introduce something which I will call as contraction phi 1, phi 2. I will denote this symbol and then I will call this as contraction of phi 1 and phi 2. This is equal to vacuum expectation value of time order product of phi 1 and phi 2. So, now you consider all pairs of the fields and then contract them. So, phi 1, phi 2, phi 3, phi 4, you have this contraction possible with phi 1 and phi 2, and then phi 1, phi 2, phi 3, phi 4, phi 1 can contract with phi 3, then normal order product of phi 1, phi 2, phi 3, phi 4, phi 1 can contract with phi 4. After that, phi 1 cannot contract with anything else, but again phi 1, phi 2, phi 3, phi 4, phi 2 can contract with phi 3, then again phi 1, phi 2, phi 3, phi 4, phi 2 can contract with phi 4, then what is left is phi 1, phi 2, phi 3, phi 4, phi 3 can contract with phi 4. Nothing else is left. However, there are terms, there are two contraction terms. Phi 1 can contract with phi 2, phi 3 can contract with phi 4. So, that will give me normal order product of phi 1, phi 2, phi 3, phi 4, where these are all two contraction terms. Then phi 1, phi 2, phi 3, phi 4, phi 1 can contract with phi 3, phi 2 can contract with phi 4, then finally phi 1, phi 2, phi 3, phi 4, where phi 1 can contract with phi 4, phi 2 can contract with phi 3. So, these are all two contraction terms. So, what you do is, in general, if there are n terms here in the time order product, this will be equal to normal order product of all these n terms, and then you consider all terms with 1 contractions, then all terms with 2 contractions, and so on. This is what goes with the name of Wick's theorem. So, in the next lecture we will use this to derive rules for evaluating the scattering amplitudes. All right.